Hello everyone, myself Anup Chandran, and in this lecture we will see how a two-body eigenvalue problem is solved in quantum mechanics. We are familiar with many one-body eigenvalue problems like the particle in a box, the linear harmonic oscillator, etc. In all these cases, the motion of the system is studied with respect to a reference point, and the solution of the Schrodinger equation of a one-body system is very easy for us to obtain. However, a two-body system is much more complicated in that it involves additional variables and motion, and therefore we cannot solve it without using some mathematical assumptions and tricks. And this is exactly what we are going to discuss in this lecture. Here we are probing one of the simplest naturally occurring two-body, the hydrogen atom. Okay, so the hydrogen atom is a two-body problem, and it will have two kind of motion. One is the translation motion of the atom as a whole, and the second is the relative motion, and the relative motion is a bit complicated than translation motion, and it is this relative motion that we were trying to understand in the previous lectures, and why translational motion is not that difficult to comprehend, and why we have given special attention to relative motion in the previous lectures. That will become obvious towards the end of this lecture. So as you can see, in the case of relative motion, the electron will move around the nucleus, and the nucleus can be considered to be a fixed point, and we can fix the origin of our coordinate system at the nucleus. And in order to study this system more effectively, we have transformed from Cartesian coordinate system to spherical polar coordinate system, and using this method we have seen in the previous lecture how we solved the Schrodinger equation. So the translational motion involves the motion of the entire atom, and therefore we have to define a coordinate outside the atom to explain this motion. And we need two position vectors, R1 and R2, where R1 is the position vector of the nucleus, and R2 is the position vector of electron, and R1 stands for x1, y1, z1, and R2 stands for x2, y2, and z2. So, and also we define the distance between the nucleus and the electron, which is modulus of R2 minus R1, and these are the coordinates that we need to define the Hamiltonian. We can now write down the Hamiltonian for the translational and relative motion as minus h cross square by 2m1 del 1 square minus h cross square by 2m2 del 2 square minus 1 by 4 pi epsilon 0 d square by r2 minus r1, which is the potential or the Coulombic interaction between the electron and the nucleus. So this is the Hamiltonian, where del 1, the Laplacian operators, del 1 square and del 2 square are defined like this. Having determined the Hamiltonian, now we can write down the Schrodinger equation, and the Schrodinger equation will have a form like this. And while trying to solve Schrodinger equation of this form, we will have some problems. We usually use the separation of variable methods to solve a differential equation, a partial differential equation like this. And however, if we follow the same steps, that is, we define the wave function like this, we will have to define the wave function like this if we are looking for the variable separable method to solve this equation. So if we write the wave function like this, we will certainly face some serious difficulties. The first thing is that the separation of variables will not be possible, because the x1, y1, z1 and the x2, y2, z2 here, they are not essentially independent. They are not independent coordinates, so the separation of variable methods won't work. And the second thing is that you will have a partial differential equation with 6 variables. So this is extremely difficult to solve now. So to overcome this trouble, we are defining 2 new coordinates, one each for translational and relative motions, and the first one is the center of mass coordinate, which is used to define the translational motion. Let's see. This is the translational motion here, and this is our coordinate system, which is outside the atom, and earlier we defined these 2 position vectors and the distance between them, the nucleus and electron, and these were all important in the earlier problem, but now we are defining a new coordinate here. We are drawing a vector from the origin of the coordinate system to the center of mass of the nucleus electron system. So this will be our new coordinates, which will be called the center of mass coordinate, and it will be defined like this: m1 r1 plus m2 r2 divided by m1 plus m2. R is a vector, and also r will be the function of capital X, Y, Z, and this X, Y, Z will be labeled like this. So this is how the center of mass coordinate system is defined. Having defined the center of mass coordinate, now we have to define a new coordinate to explain the motion, the relative motion of electron and nucleus. So for this we define r, which is the distance between the electron and nucleus, and from the discussions that took place so far, we know that the potential is dependent on this distance, and therefore we will have to define r to explain the Coulombic interaction between the electron and the nucleus. So this is the earlier coordinate system with which we are familiar. In the previous lectures also we have discussed this, and in the beginning of this lecture we have seen how these coordinates are very important to define the relative motion between electron and nucleus. So your r will be dependent on small x, y, z, which are the coordinates given here. Thus we have defined 2 new coordinates, capital R and small r. Using it we can define the entire motion of the hydrogen atom. So the advantage of defining these 2 new coordinates is that now we will be able to convert a 2-particle complicated equation to 2 1-particle equations, and also the separation of variable methods can now be realized. So this is your the coordinate system that we were using earlier to define the relative motion of nucleus and electron. Now we have defined r, small r, which is which can define the entire motion, entire relative motion, and it was your earlier coordinate system which was used to explain the translational motion, and now we have defined capital R, which is sufficient enough to explain the translational motion of the hydrogen atom. Now that we have defined 2 new coordinates, it is time for us to write down the Schrodinger equation for the system. For that we have to first find out the kinetic energy and potential energy corresponding to each type of motions. So in the case of translational motion, we actually observe the translational motion of the hydrogen atom from somewhere outside the system, like this. So your coordinate will be outside the hydrogen atom. You will be looking at it from the outside world, and when we observe it, we consider the mass of the system to be simply the sum of the individual masses of electron and nucleus. That is, mass will be m1 plus m2, And also we know that the translational motion only has kinetic energy, because here we are assuming that no external forces are acting on the system, that is no magnetic or electric field or any other kind of force is acting on this hydrogen atom. This is completely isolated, and in that case you may be able to write down the kinetic energy as minus h rho square by 2m into del square r. R stands for the this vector, and your Laplacian operator is this. The potential energy will be 0. For relative motion, we fix the origin of the coordinates x, y, z at the nucleus, and we study the system from within the hydrogen atom. That is, we are inside the hydrogen atom, and for us the nucleus would appear to be stationary and the electron can be seen moving around it. And to reduce this two-body problem into a one-body problem, or to treat this two-body problem similar to a one-body problem, we have to define the reduced mass of the system, which is given by mu equals m1 m2 divided by m1 plus m2. So this is a common trick that we use to solve many two-body Newtonian equations, and after defining this, we have to now consider the Coulombic interaction between electron and the nucleus, and this interaction, this potential, will be minus 1 by 4 pi epsilon 0 into E square by R. So it must be noted that the potential here is independent of the center of mass and is only dependent on the distance between the nucleus and the electron. And now the kinetic energy of the relative motion in this case will be h cross square by 2 mu. We are using mu instead of m1 or m2 here into the Laplacian operator. This is the kinetic energy operator, and the Laplacian operator is given here. We are now in a position to write down the time-independent Schrodinger equation of the system, and this equation is like this, and this is labeled as equation A. And this psi here is the wave function of the system, and it is dependent only on capital R and small r. Since capital R is defined or used only to explain the translational motion of the system, while small r is only used to study the relative motion of the nucleus and electron, we can use the separation of variable methods to solve this partial differential equation. That is, we can write down the wave function as a product of two functions, while each function will be a function of a single variable. That is, this function will be dependent on capital R, while this function will be dependent on small r alone. So substituting this wave function in the above partial differential equation, that is equation A, we will be able to separate it into two equations. So these are two one-body equations obtained from this two-body equation, and to obtain these we have to use some mathematical tricks that we have already discussed in lecture 1A and 1B of the hydrogen atom. Okay, so this equation here is nothing but the free particle Schrodinger equation. This equation describes the translational motion of the system, and its solution is very straightforward. Our equation C here is a bit complicated, and we have to use spherical polar coordinates to solve it. It is this equation, the equation of relative motion, that we were discussing in the previous videos 1A and 1B. Thank you for listening.